Um, we will just resume, just rejoin the same link. I'll be back within a minute. And yeah, I'll get into it. I don't have like that much this week since we are a bit time pressed. But yeah, as always, you can privately message me or the TAs, and I should have enabled messaging to everybody. All right, let me see. And make sure not to interrupt the class and to message answers privately. Privately. Okay, so let's go over the homework. So using only the digit 2, how many 2's must be used to create a number that's divisible by both 9 and 11? So this kind of cuts into today's topic, right? But the divisibility rule by 9 is that all the digits, the sum, if has to be divisible by 9 for the number to be divisible by 9. We'll prove this later on. For 11, if we have like 2, 2, 2, 2, we do 2 minus 2 plus 2 minus 2. This is like alternating sum. This is equal to 0, and 0 is divisible by 11. So 2, 2, 2, 2 just happens to be. So the rule for 11 is like alternating sum difference gives something divisible by 11. Now, if you want to satisfy both of these simultaneously, first notice that if it's a number that's all 2's, to satisfy the 11 condition is pretty easy. We just need an even number of 2's. For 9, well, 2 is not like 2 is relatively prime to 9, so we know that we're gonna need like some multiple of 9 2's, and to satisfy both these simultaneously, smallest one is 18 2's. All right, yeah, and as always, I'm going over the homework problems myself to save a bit of time, and yeah. Using only the digits 1, 2, and 3 with at least one of each. What's the smallest integer created, which is divisible by 8 and 9? Okay, so we already went through the divisibility rules for 9. Oh yeah, to the person in chat, please use your real name. Anyways, so we already know 9. What about 8? Well, 8's the last 3 digits have to be divisible by 8. Why is this? Because, well, if you have like some number A, B, C, D, E, F, we're claiming that you only need to check if DEF is divisible by 8. This is because this number is equal to essentially ABC, the 3-digit number ABC in this case, times 1,000. And this is guaranteed to be divisible by 8. So we only need to make sure that this part we add on is also divisible by 8. And similar results for other powers of 2, like 4, you just check the last 2 digits, 16, the last 4 digits. But anyways, so we do casework. Well, we know like the number's got to be even. The last digit is going to be a 2. Sorry, it's going to be 2. It can't be 22 because that's not even divisible by 4 in that case. So it's going to be 12 or 32. If it's 12, well, either option works actually, 112 and 312. You can verify that this is 8 times 14. While this should be 8 times, I believe, 39. So yeah, anyways, for each case, let's take the 112 case first. So we've already satisfied our like at least one of each condition by having a 1, a 1, and a 2. Now, we'll see like that why this is true when we prove why the divisibility by 9 works. But it turns out that actually the sum of the digits mod 9 is congruent to the numbers remainder divided by 9, or mod 9. So 112 is 4, or mod 9. You can test this because 108 plus 4, and this is multiple of 9. So we need to add some like digits that will sum to something equivalent to 5 mod 9. Well, let's do that. The smallest way would be 2 and 3, using the digits we have on hand to make 5 mod 9. And of course, we want smallest first, right? Because we want to minimize this number. And this satisfies everything so far. Because like there's 1, 2, 1, 3, and 1, 1, and 2 1s. I mean, there's at least one of each, sorry. 2 1s, 2 2s, and 1 3. Whoops. And thus, this number is the smallest for this case. For 312, Okay, so we want the other stuff to sum to, in this case, 3 mod 9 to make this, which is 6 mod 9, convert to 9 mod 9. For that, we can just like peg a 3 on here, right? Because 3's can go into 3 mod 9. This also works because like 3112 already satisfies like the digits we must have. Oh yeah, for this case, 32 is divisible by 8, so the only choice is 232 for the last 3 digits. You want to make this number divisible by 9. This part is 7 mod 9. We need something that's 2 mod 9. We think 2232, but remember, we need to use a 1 somewhere in there, so we can't do that. And the smallest would actually be 1132, which is still a lot bigger, that a whole order of magnitude bigger than this. So 3312 should be our answer. So those should have been pretty straightforward. It was just kind of, I guess, understanding. Okay, a Canadian moose. First of all, can you please change your name? And second of all, what's your question? If you have any.
Okay. My thing was I can't. You kind of can just guess and check for the last one.
Yeah, I guess so, but like that would be in my opinion, that's like less systematic, and it's kind of hit or miss on the actual test when you encounter such problems. So I would encourage you not to for a problem like this. For a simple problem, like maybe a small word problem, that would be a good idea on the AMC 8 though. It really depends on what you're doing. So anyways, let's move on. A bag contains $1, $2, and $5 tokens. Number of $1 tokens in the bag is equal to the number of $2 tokens, and there are 18 $5 tokens. The expected value for the number of a drawn token at random is $2.25. How many tokens are in the bag altogether? Let's assume that this is exact. Okay, so total, if there's like X $1 tokens, then we have like probability, the expected value, if we remember what that is the probability time of getting it times like the thing itself. So for $1 tokens, that would be X over 18 plus 2X. For $2 tokens, that would be 2 times X over 18 plus 2X. I mean, plus 5 times 18 over 18 plus 2X, which gives our final fraction as 3X plus 90 over 2X plus 18. And we say that this is equal to 2.25, which is equal to 9 over 4, really. 9 over $4. See, we can cancel 3. And then we just cross multiply. Oh, we can also cancel a 2 from these. So we have 2X plus 60 is equal to 3X plus 27. Solving, we just get X equals 33, and you can confirm by plugging back in that this works. So the fourth problem, you have concentric circles, radii of 3, 4, 5, and 6. What's the probability that a random point selected within the large circle is in one of the shaded circles? And I believe you were given the following diagram for this homework. It was something like this. Where let's try and mark this. This is not drawn to scale, but this is 1. This is also 1. This is 1. And then this is equal to the diameter of the 3 centimeter one, which is 6. So what's the probability random point is one of the shaded regions? Okay, well, there are two shaded regions here between 5 and 6 and 3 and 4, right? So the area of each of these pi times 6 squared minus 5 squared, and the other one's pi times 4 squared minus 3 squared. For total of this is 11 pi, and this is 7 pi. For a total of 18 pi. And the total is, if it's in the range of the large circle, 36 pi. So then our answer is just 1/2. This is kind of probability, not quite sure why I was thrown in this section, but yeah, it's not too difficult. Okay, so now we're gonna go into primes and divisibility, which we did discuss last week. So a prime is a number divisible by only itself in one, and a number is more, and so has two factors, one in itself. Other numbers are usually consistent of more than two divisors. And we call this number a composite. Our special case is the number one. Well, since one is, I guess, well, one times one in terms of integers, there's only like one distinct factor here. Nobody doesn't really belong in either category. Uh-huh. Yeah, okay. So then these are the categories of numbers, prime and composite. Primes are like very important in number theory for various reasons and properties that they have. And to find them, well, you can just start with a list number, say 1 to 100. Well, and then the first prime you encounter and the only even prime is 2. So we then cross out every multiple of 2 from like 2 to 120. In this case, I use 120. So after to the next biggest number that's not crossed out would be 3. We do the same process for 3, crossing out 6, or 6 is already crossed out. We crossed out like 9, 15, etc. Right? And then we can just go, we just see 4 is taken, is crossed out. We know 4 is not a prime. We go to the next one, it's not crossed out, it's 5. And we repeat the same process over and over. Eventually, we'll start getting left with chunks that only whose only non-crossed out elements are primes. And this is called like this is called the seeds of Aristophanes. That's right, which you may have heard of. It's like fun, but also quite impractical. But it was a first step toward an algorithm that could actually like detect and check a prime number. So we will review the divisibility rules and also why they work. For numbers less than or equal to 10, well, we already know, it's memorized. It has a 1, it's usually divisible. 2, the last digit's even. The last digit sum of 3 is divisible by 3. The last two digits is divisible by 4. And if units digit is 0 to the 0 or 5, it'll be divisible by 5. For 6, the last side is even, the last digit is even, the sum of the lights is divisible by 3, which is basically a combination of rules for 2 and 3. And there's this one more complicated one for 7. We won't get into it. I believe it's something like you chop off the last two digits of the number, and then divided by 2, no, divided by 7, and then it like gives you something. But we're not, well, most of you don't really need that. 8 we already discussed, similar to 4, it would be the last 3 digits, 16 it would be the last 4, etc. 9 is very similar to 3 for actually the same reason why its divisibility rule works. For 10, the last digit is 0. Okay, so now before we do the example, I guess I want to show you I guess how you prove like some of these divisibility rules. So here we have to do for base 9. Let's do some modular arithmetic. Let's say your number is like A, B, C, D, base 9. So then we have A times 9 cubed plus B 9B squared. 9C plus 9. All right, so after this, what happens? Or sorry, this is base 9. I was thinking something slightly different. So yeah, no, sorry, this is a bit different. Okay, so if numbers like A, B, C, D, E, F, mod 9, this is A times 10 to the like 5th, B times 10 to the 4th, C 10 to the 3rd, D 10 squared, E 10, and F 1. Okay. Now note that like that this will make these 10's powers 10 is 1 mod 9. So these will always be 1, and we're just left with the number itself expanded like this is congruent to A plus B plus C plus D plus E plus F. The reason why is like, as I just mentioned, 10 is 1 mod 5. That's just like a modular arithmetic thing where you can take the power and it'll preserve like that. Similarly, 10 is negative 1 mod 11, meaning remainder 1, meaning it's 1 less than a multiple of 11. So then then it would be A times 10 to the n minus B times 10 to the n minus 1 plus C times 10 to the n minus 2 plus dot 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 is equal to the number. So because of this, we can like derive the divisibility test for 11 in much the same way that the divisibility test for 9 was discovered. 10, the last digit is 0 for that divisibility. And of 2, 3, 4, 5, 6, 8, 9, which one divide 3, 4, 3, 5, 8, 6, 4, 7? What about 1, 2, 3, 4, 5, 6, 7, 8, 0? All right, now I would love to hear your interesting answers about this. And also ask the TA Ethan, who is with us today. I'll give you all like several minutes to do this problem. You can private chat your message to me once you're done, and I'll get around to it eventually. Mm. All right, so it looks like we got several answers. Yes. Okay. So does anybody want to go over this? Sure, Lewis, you can go ahead. One or both, your choice.
I will do both.
Okay, go at it.
So, like for number one, we can because four is even, two is good. 3 plus 4 plus 3 plus 5 plus 8 plus 6 plus 4 mod 3 is remainder is 0. So 3 is good. 64 can't like 64 can divide 4, so 4 is good. 4 is not a multiple of 5, so no. 6, it can divide 2 and 3, so yeah. 8, 864 can divide 8, so yeah. 9, it can't divide 9, so no. And then 10, no, because the last digit isn't 0.
Yeah, that's right. Good use of divisibility rules. It's obviously even. Two's in the bucket. 64 is divisible by 4. Thus 4 is also in. If you sum up the digits, you get 3 plus 4 plus 3. Plus 5 plus 8 plus 6 plus 4. These sum to 18. These sum to, I believe, 15. For a total of 33 mod 9, which makes it divisible by 3. Which makes it divisible by 3 and not divisible by 9. I should have mentioned here that this this proof, like, as a direct consequence of it, uh, since this is the number itself is congruent to the sum of the digits mod 9, this like works for anything. Same thing for mod 11. Only if you do it in the right order though. If you like start from a certain, you have to start from like with the right sign, depending on to get the number mod 11. All right. So yeah, just a small cautious note, especially for 11. And as he said, you can check 864. You can pretty clearly tell is divisible by 8. And yeah, so that's basically it. And obviously it's not divisible by 5. If it's not divisible by 5, you don't have to check if it's divisible by 10, because like, it has to be divisible by 5 before it's divisible by 10. Same thing with 2, 3, and 6. If it's divisible by 2 and 3, 6 is automatically a factor of it too, since 2 and 3 are relatively prime. Now, Lewis, you can go ahead about 1, 2, 3, 4, 5, 6, 7, 8, 0.
So like 1, 2, 3, 4, 5, 6, 7, 8, 0. 0 can divide 2. So yeah.
Yeah, I would suggest you like check your microphone. I think there's like some issue. All right. Yeah, I think Lewis might have a. Do you want to try again? there's like a really loud scraping noise through the microphone. Okay, yeah. I
Can you
don't
hear
think
me?
it's. Yeah, I can hear you, but it's not very good. Yeah, I think you should just mute. All right. Oh, sorry, I was muted. Sorry. Okay, so now let's just check 1, 2, 3, 4, 5, 6, 7, 8, 0. Some of the digits of it. What is that? Okay, well, if you know your like n times n plus 1 over 2 formula as well, 8 times 1 over 2, 6. So, and this number is even, it's divisible by 4. So we automatically can knock down 2, 3, 4, 6, 9. We also know it's divisible by 5 because like it ends in a 0, and 10 as well, because it's obviously even. We notice 780 is 4 times 195, so it's not divisible by 8. And that's like pretty much it actually. 1, 2, 3, 4, well, of course 1. 1, 2, 3, 4, 5, 6, 9, 10. So yeah, that's basically how you do these kind of problems. Use like sum of digits. Remember the various divisibility rules for 9, 11, powers of 2, and for 5. Since we work in base 10, this is why the rules for 5 and 10 are so convenient, because they're like the key prime factors, or like numbers that are that divide 10. So now we'll see some harder divisibility. You will often see problems that require specific constraints on the digits and what numbers will divide it. In these cases, it's helpful to use divisibility rules to make deductions. So we have some more example problems. You can work on these for a second, and then I'll check your answers off eventually. Or you can send it to TAU. I think you should be able to message him. Oh yeah, if you have any problems messaging any of us, you can, in that case, you can just unmute and or just randomly chat that. But anyways, so what's the smallest 4-digit number divisible by 2, 3, 4, 5, 6, 8, 9, and 10? And hint for this, think prime prime factorization is what I meant to say. As well as like what these imply in terms of the digits. I guess like in this case, divisibility rules are a bit more helpful. But anyways, using only 1s and 2s, what's the smallest integer you can create, which is divisible by both 3 and 8? All right. So yeah, I'll set you this. I already see some answers, and it seems like they are right. All right. So does anybody want to like present number 1? Because like I see a lot of people doing that. Sure, Nathan, you can go. Starting.
You? Well, 1080. Well, something that I kind of memorize is that the LCM of 1 to 10 is 25, 20, or that means that like so like so it's like 8 times 9 times 5 times 7. It's kind of like that. And then I just kind of divide it by 7 to get 360. So that's like, so it's the smallest number that's divisible by all of these. And then I just multiply it by 3 to get 1080.
So he's on the right track here in his explanation, although there are a few things to, I guess, tighten up. So when I said like prime factor, think about that. You want to notice that like some of these are kind of redundant conditions, like 2 and 4. If it's divisible by 8, you're guaranteeing both of these, right? So you want to, in particular, what you want is to guarantee all of these at once is that it must be divisible by their the LCM of these numbers. And you don't have to memorize because like for small numbers, you can prime factorize and to find the LCM relatively easily and disregard a lot of like redundant stuff. So the LCM would be 2 cubed, the highest power occurring in 8 times 3 squared occurring in 9 times 5. And really, if you look at it, there are no more prime factors because there's no 7. Everything here is made up of 2s, 3s, and 5s, right? This is equal to, I think, as he said, 360. So what we really want is like the smallest 4-digit multiple of 360, which he said is just 360 times 3. That's equal to 1080. So yeah, there you go. That's your answer. And how I get it. So really, I guess this is more of like thinking about LCM and stuff than just divisibility rules, although I'm sure you could take an alternative approach to it. So we have another example using only 1s and 2s. What's the smallest integer, smallest you can create, which is divisible by both 3 and 8? All right, so I see, let me just 1 second. So I see a couple of correct answers in chat, so I guess I'll just go over this too. We want it to be divisible by both 3 and 8, and only 1s and 2s. If we think about it, the only possible digits this can end in is 1, 1, 2, because divisible by 8 means divisible by 4, and it has to end in 2, first of all, since it's even. So it can only be 12, otherwise it won't even be divisible by 4. 12 is the last 2 digits, and only 1, 1, 2 will be the ending that makes it divisible by 8. So we want to add like, we want to minimize the number of digits we peg on over here. And then we want to minimize the digits in like the order that they appear. So to make this divisible by 3, we look, oh, this is 4 mod 3. We want to add like 2 mod 3. We just put a 2 here. So we get 2, 1, 1, 2. Honestly, this is kind of like an easier version of that homework problem we gave with the 1, 2, and 3. But yeah, just think about divisibility rules, what sums need to happen. And I kind of assumed that like the sum of the digits of a number mod 3 would be equal to the number mod 3. But really, this is just follows the same line of reasoning as the mod 9 proof, since 10 is also congruent to 1 mod 9. All right, so for 7 and 11. 11 I already covered and alluded to, but they say it's a bit more complex. I really don't think so. As long as you like remember it right and understand how like you get to 11 at least. For 7, it is a bit more complex. You separate the units digit and last digit from the rest of the number. As an example, for 224, you split it into 22 and 4. Then subtract 2 times the last digit from the remainder. In this case, you have 22 minus 4 times 2 is 14, which is divisible by 7. So 224 is divisible by 7, which is actually 14 times 16. So it would be, I believe, 7 times 32. For 13, you can do something similar except multiply 4 and add it, but it is rarely important. You can repeat the process if you still don't know. Really, like these divisibility rules, I find that they're just taking advantages of multiples of these numbers that are close to some power of 10. For example, let's say you have like some number, I don't know, A, B, C, D, E. I think 5 digits is good enough. So they're taking advantage, I think, here of the fact that like 100 is equal to 98 plus 2, which is like, of course, 98 is divisible by 7. 7 times 14. And one way you can use that is like you first like consider these and then this too, and this separately. Although I think that gives a slightly different rule. There's a rule where you chop off like the last 2 digits and check the rest. But anyways, we can like cover those rules later sometime if we have free time. For this rule, to derive this, like So we have some number, I don't know, let's just go with A, B, C, D this time. We want to split it into A, B, C, and D. We want to subtract 2 times the last digit from the remainder. In this case, it is important to write that this number is 10 times A, B, C plus D. And what we're claiming is that if we subtract ABC minus 2D is 0 mod 7, then this is 0 mod 7. Okay, so how do you get from here to there? So for the sake of proving it, I'll just show you guys what this is probably more than you need to know. So if 10 ABC plus D is congruent to 0 mod 7, which is what we want to find out whether or not that's true. Then we just write this is congruent to negative D mod 7. 10 is just congruent to 3 mod 7, remainder of 3. Notice that if we multiply both sides by 2, we get 6 ABC, and 6 is congruent to negative 1 mod 7, so we should multiply both sides by 6, sorry,